In this section of the course, we are going to look at how deep learning can be used for recommender systems. This lecture will discuss the theory behind how deep learning can be applied, and following that, we will look at the code. To start, I want to talk about recommender systems as a general concept. Where can we find recommender systems and what is their purpose? I think you'll be surprised to find out that recommender systems are one of the most applicable machine learning concepts ever. It's a type of machine learning that can be used by nearly any consumer-facing business, and you most certainly encounter recommender systems multiple times daily. Let's start with the first website everybody goes to when they go online, Google. Google Search is in fact a recommendation engine. Actually, when you perform a search, multiple recommendation engines are working to build the page that you see. Not only do you have the search results, which are recommendations based on your query, your geographical location, and maybe even your search history, but don't forget that Google is also an advertising company. The online advertisements you see when you go to google.com are also recommendations based on your previous browsing history. Another great example is Amazon. When you search for a product on Amazon, it's more likely that you'll see advertisements for similar products in the future. You might also see recommendations for related products. For example, if you're buying an iPod, you might also be in the market for new headphones, a case, and a screen protector. Another great but seriously unfortunate example is the news. News sites employ recommendation systems, and they even do A/B testing on their article headlines to improve click rate. This is very unfortunate because this means that news has become more biased and more polarizing over time. People don't care about boring news, they want to read something exciting. And news companies are more than happy to give that to you in place of real, factual, and unbiased news. There are really too many examples of recommendation systems to mention. Here are a few more examples to help you internalize what exactly it means to recommend. We have Netflix, which recommends movies and TV shows. We have YouTube, which recommends videos. We have Reddit, which recommends a mix of user-generated content and third-party content posted by users. We have Facebook, which sorts your newsfeed based on what will make you stay on it the longest. Closely related to that, we have Instagram, which is owned by Facebook, and it does largely the same thing. You're shown a feed of Instagram posts that are recommended in order to keep you engaged. In this lecture, we'll be focusing on a specific kind of recommender. This recommender works on data that comes in the form of triples. The three items that form a sample are the user, the item, and the rating that the user gave that item. As an example, suppose you're creating a movie recommender. Here are what a few rows of your dataset might look like. Alice rates Avatar a 5. Bob rates Star Wars a 4.5. And Carol rates The Godfather a 4. So all of our samples will look like this. The first item is the user, the second item is the movie, and the third item is the rating. One important feature of this type of dataset is that it must be incomplete. Why? Well, think about it. If all users have already watched and rated all existing movies, then what would there be to recommend? If I've already watched and rated every movie in existence, there's no need to recommend anything to me. You can't recommend a movie to me because I've already seen it. Luckily, for any real dataset, this won't be the case. Imagine you have 1 million users and 100,000 movies, which is not unrealistic. You can probably count the number of movies you've seen in your life, and it's probably a lot less than 100,000. The number of movies you've actually bothered to rate is probably even smaller. The question now is, once we have such a dataset, how does it help us make recommendations? Let's take a very simple example. Consider Bob. Bob rated every movie in the Star Wars series a 5. Bob also rated a few of the Star Trek movies a 5. And Bob also rated Avatar a 5. Common sense tells us that Bob is probably a fan of sci-fi. Bob likes movies that have space travel, aliens, and so forth. It is probable then that Bob would like movies that have the same features. A pretty obvious recommendation for Bob would be a Star Trek movie or TV show that he hasn't seen yet. Let's try to generalize this concept. As you know, we're given a dataset that consists of triples containing users, items, and the user's ratings for those items. Suppose we can fit a model to this data. Let's just call it F. F takes in two arguments, a user U and a movie M, and it outputs a predicted rating. There are two things that we would like this function to do. Number one, obviously, if the user, movie, and rating appear in our dataset, then we would like the predicted rating to be close to the real rating. And number two, we would like this function to be able to output a predicted rating, even if the rating did not appear in our training set. Luckily, a neural network is a perfect model for this use case. As you know, a neural network is a function approximator. It fits to the dataset so that when it makes predictions, those predictions are close to the training targets. But not only that, it can also make new predictions for data which did not appear in the training set. So how might we use such a model to make recommendations? Well, here's one strategy. Once we have a model that can predict ratings, this becomes easy. For a given user, predict a rating for every movie that they have not yet seen. Then sort these movies by predicted rating. The movies you want to recommend are simply the movies with the highest predicted rating for this user. Pretty simple. The next question is, how can we go about building such a model? We know that we need a neural network of some sort. But here's a problem. Both users and movies are categorical objects. Neural networks are basically a series of matrix multiplications. As you know, we can't multiply a categorical object by a number. What is Star Wars times 5? This does not make sense. Luckily, we have encountered this problem before. Strangely, natural language processing is the field we draw inspiration from in order to build deep recommender systems. As you know, in NLP, the main input is words. Words are categorical, they cannot be multiplied by numbers. So what do? We use an embedding. Recall that an embedding is a mapping from each category to a feature vector, which is essentially a list of numbers that can be multiplied. Here's how we might use a neural network for recommender systems. Let's say we have an input user Bob and an input movie Star Wars. The first thing we do is map both the user and the movie to their respective embedding vectors. So I have a vector for Bob and I have a vector for Star Wars. Now, usually these embedding vectors are the same size, but this need not be the case. So now both Bob and Star Wars are represented by feature vectors. The next thing we do is concatenate these two feature vectors into a single feature vector. Once we have a feature vector, the rest is obvious. We just do the same thing we've always done, pass this through a neural network. Since this is a feature vector and not some special object like an image or a sequence, we can use simple ANNs rather than CNNs or RNNs. For recommender systems, the final output layer will be a linear regression with no activation function, since predicting ratings is a regression task and not a classification task. As a point of interest, I said earlier that we can use NLP techniques to inspire models for recommender systems. In fact, the opposite is true as well. Recommender techniques have been used in NLP. My favorite example of this is a technique called matrix factorization. Matrix factorization, which we haven't talked about, is an algorithm that has been known for quite a while in the field of recommender systems. Around the time word embeddings were becoming popular, specifically due to the algorithm known as word2vec, another similar algorithm came out called GLOVE. GLOVE essentially solves the same task as word2vec. It's an algorithm for finding word embeddings. Using these word embeddings, you can do all sorts of fun analogies, such as king minus man equals queen minus woman. Well, it turns out that GloVe is nothing more than matrix factorization, just an old technique from recommender systems. So it's always good to study techniques from different fields, because you never know when what you learn can be applied to your own work.